Okay, so this is section 3.2, right? We're going to talk about logarithmic functions and their graphs. And we went over the exponential function last week, right? So where you've got something like this, f of x equals a to the x, and that's not mine. All right, very well. And for this one here, we said a is got to be greater than 0. A cannot equal 1, right? So we had a couple of things. That x is any real is the real number. So this week we want to talk about what's the inverse of the exponential function. So if you look at if you guys remember when we were looking at inverse functions, we had that vertical line test that we did to make sure that it could have an inverse function. And basically, there had to be a one-to-one relationship between all the points. Because remember, when you do the inverse function, you basically take all the x and the y coordinates of one graph and you flip them around. Because the inverse will always be, like if this is your graph here, then the inverse of it will be this graph here. Okay, it flips around that line that says y equals x. And so basically every point that's x and y here will be in this order, y and x here, and vice versa. All right, you flip those around. And so we're going to talk today about the function that is the inverse of the exponential function, and it's the logarithmic function. And so let me write that definition on the board. I guess I should write a title here, logarithmic function. For x greater than 0, a greater than 0, and a not equal to 1, y equals log little a x, if and only if x equals a to the y power. The function f of x equals log base a of x is called the logarithmic function with base a. All right, have you guys worked with logs and exponential functions before? So make sure that you understand this right here, these are equal to one another. All right, they're equivalent. Y equals log a of x, and x equals a to the y power are equivalent. And so that means if you have something like this, log 2 to the 8, or it's log base 2 of 8, you know the answer to that because you know that if I say 2, if this equals, let's say if this whole thing here equals b, then I know b has to equal 3 because 2 to the third power equals 8. Let me write it like this. Let me take the b out altogether. All right? Yeah. So think about this. Log of base a, our base is 2, okay, of x. Log base a of x, which is 8 in this case, equals 3. 3 is our y. All right? Now if we take this here and we say whatever was a, which is the 2, and we raise it to the power, which is the y here, 2 to the third power equals 8, which is the x. Does that make sense? So if I give you a problem, if I were to say what is log base 2 of 4? You would say, well, 2 to what power equals 4? And 2 squared equals 4, so you would say that equals 2. Does that make sense? Mm-hmm. So take the little guy here and say, what power do I need to raise that guy to get this number here? So there's several examples, in example 1 here, 4 of them, where you can try your calculator. Well, this isn't a calculator one, never mind. This was just looking at it and figuring out the answer. So if we look in the book here, just quickly, log base 2 of x, and they tell us that x is equal to 32, and so we're basically trying to figure out what power do I raise 2 to get 32. And so log base 2, 32 has got to equal 5 because 2 to the 5th power equals 32. Right? So that's how you need to think about those. Like I said, that's because we need to realize that these here are equivalent to one another. We can rearrange it to be this. Again, making sure that you're grasping it. Log base 3 of, is it 1 that they have there? Yeah, log base 3 of 1. We're asking ourselves 3 to what power equals 1? 0. It's got to be 0, right? Log 4, log base 4 of 2. So again, we're saying 4 to what power equals 2? Like half power, right? Because that's square root 4 to the half power is the same as the square root of 4, which equals 2. All right, everybody, that makes sense to everybody? Log, I guess, yeah, make sure that you realize this too. Log 10, base 10 of 1 over 100. So 10 to what power equals 1 over 100? And so this is 10 to the negative 2 equals 1 over 100. So this equals negative 2. So just remember that with your exponents, right? Excuse me. 10 to the negative 2 is the same as 1 over 10 squared. You just move your exponent to the bottom and get rid of the negative sign. Everybody follow those? Now, your calculator is only going to have a log button for log with base 10, right? And so that's what the next example was about, example 2. They just give you a lot of examples with log of base 10. That's what your log button on your calculator means, right? It's log base 10 is what it's calculating for you. So if you do log, if you look in example 2 in the book, they want you to do log base 10 of the number 10. And so you enter that in your calculator by clicking the log button and then entering 10 and then hitting equals. Excuse me, and you'll get 1. So this is how you enter in this problem here. And so just make sure that you can do all of those, right? If you do log of 2.5, you should get 0.3979.
So we use the log button, and then do we just type 10 to power 10?
The log button and what?
The log button, and then we just type 10, and then we go up to power 10. Is that how it works?
No. You just type log 10, and you're done.
Oh, that's it?
That's it, yep. So if you're going to figure out, just so it won't be confusing, if you're going to find log base 10 of 5, what you type in your calculator is just your log button and the number 5. Because the log button means log base 10. Does that make sense?
Mm-hmm.
So make sure you can get all of those. If you know how to enter that in your calculator. Oh, I never checked your homework, nor did I hand out the test, did I?
No.
Can you guys get that out for me real quick? I'll pause this. All right, so let's look at some properties of logs, of logarithms. And hopefully these will make sense as we kind of think through them. Log base A of 1, that's got to equal 0. Right? Because we're saying A to what power equals 1. And that's always going to be 0. All right, so make sure you recognize that. Like you say, because A to the 0 equals 1. Log base A of A has got to always equal 1 because it's A to the 1 that equals A. Right, these next two are going to be really important as we continue to explore these types of functions and in particular start solving equations with these functions in them. Log base A of A to the x equals x, and A to the power of log base A x equals x. And that's because we said at the beginning that the log and the exponential function are inverses of one another. Right? If you think back to when we worked on inverses, how do we prove that two functions are inverses of one another? Well, we plug one into the other, and we should always get what value? You guys remember that?
1.
No? X. Right? You're on the right track. It was x. And so then if we flip it around and do it the other way, we should also get x. Right? And so it makes sense. What am I doing here? Well, I'm taking the exponential function and I'm plugging it into the log function. So I get x. And here I'm plugging the log function into the exponential function, and I should get x. So because they're inverses of one another, that's true. And then finally, if log base A of x equals log base A of y, then we can say that x equals y. And this is true because of the one-to-one property. It's that idea that if you plug one value in, since it's a one-to-one function, that means that for every x value, there's only one y value, right? And vice versa. And so because that's true, then we can draw this conclusion here. Log base A of x equals log base A of x equals log base A of y, and then we can say that x equals y. All right? And so they just give us a couple of quick examples to apply these properties, and they say log base 2 of x equals log base 2 of 3. And so what does x equal? Well, based on property number 4, x has to equal 3. What about this one here? Log 4. Log base 4 of 4 equals x. And so what is x? 1. 1's based on this property here, right? Log base A of A equals 1, so x equals 1.
Oh, because 4 and 4 are the same, right?
That's right, because they're the same. and then log base 5 of 5 to the x power. And they want to know what that is, and that's going to equal x. And that's by this one here. So it's like the log, they sort of undo one another, right? It's kind of like thinking about the opposite of like division undoing multiplication and subtraction undoing addition and stuff like that. Like if you take log base 5 of the number 5, whatever power it's raised to, that's the answer that you get. All right? So kind of think about it that way, because as we start solving some equations, it's going to be important that you kind of process it like that in your minds. And then finally, 7 to the power of log base 7, what's the number, 14?
And that's just the second part of property 3. That's just the 8 of the log.
That's just this one, right? So it's just going to be 14, right? I'm sorry, I've been a little stingy today. I forgot, guys. When you guys questioned whether or not I'd make 100 on the test, it just sort of threw me off. You know, my mind's been foggy ever since then. All right, any questions about applying those properties? Does that make sense? Something that maybe would be on a note card, I'm thinking. So graphing log functions. I'm just gonna jump past this pretty quickly and just make the comment that if we've got the function y equals log base a of x, right? And we recognize that that is, well, let me do the real one I do here. So they have log base 2 of x, and they say that they first have us graph, they say that's g of x, and they first have us graph f of x, which is 2 to the x power. So one's the exponential function, and the other is the log function. And so based on what we know, understanding that these are inverses of one another, right? We don't have any way to plug this in our calculator, log base 2 of x, right? But we do have a way to plug 2 to the x in our calculator, right? And we can plot points and we can graph that. And if we remember that because of the way this is written, that this function is the inverse of this function, right? Then we know that these guys are going to be, one's going to be the reflection of the other about this line right here, y equals x. Okay, so if we plot f of x equals 2 to the x power, we come up with a graph where you've got a point here at 0, 1, and then you've got another one at 1, 2, and they plotted one at looks like 1/2, -1, 1/2, so they plotted one here. So if we've got a function that looks like this, and we know that that's 2 to the x power, then for every point that we have here, since this point here is 0, 1, then we just reverse those, and we know that we're going to have a point at 1, 0 for the corresponding log function. Okay, so 1, 0, we know we're going to have a point here. And since this point is 1, 2, then we know we're going to have a corresponding point at 2, 1. All right, so this is 2, 1 here. So we got a point there, and then finally this is -1, 1/2, and so we know we're going to have a point at 1/2, -1, so a point like around, did I do that right? Did I make a mistake somewhere? -1, 1/2, -1. Oh, I did, it's this right here. I wrote down 2, 1, but I plotted 2, -1. This should be 2, 1, there we go. All right, 2, 1. And so I know then that the log base 2 function is going to be the reflection of that, and it's going to look like this. And so you guys see how I did that? I picked a few points for this guy, the 2 to the x, and then I just flipped all of those points and created the other. Right? Any questions about that? We're going to learn how to, we actually are going to learn how to enter this in our calculator, how we can do log to different bases in a moment. So there's a way to get around that, but there's no like direct key on your calculator. You have to basically split it up into like a division problem. So you can do it that way. We also don't forget, you know, that all of our transformation stuff that we've already learned still applies. So they show us that in at the top of page 195. They have the parent function log a of x, log base a of x, and you know, we can plot points for that guy, and we see what it looks like. But just remember, if you have if you know the function log base 10 of x, for example, and then they tell you to plot log base 10 of x minus 1, well, that's a transformation of log base 10 of x, right? And so we just, the whole graph will be shifted 1 unit to the right because it is log base 10 of x minus 1. Because we have x minus 1, it's shifted to the right. And if instead you had 2 plus log base 10 of x, then it would be the graph of log 10 of x and everything shifted up too. All right, so don't forget your rules for being able to transform functions that way. We need to talk about, any questions about that overall? So you know, when we talked about the exponential function, we learned about the special value e, which was, I don't remember, 2.78 maybe, something or another. I don't remember what e was.
The natural value of e or something.
What's that?
It's just e. I just remember it as e.
Yeah, it's kind of like pi, right? It's just equal to some decimal value, and it's on your calculator, so you don't have to remember the numbers. Well, just like we talked about that when we talked about the exponential function, we're also going to talk about the inverse of that, which is the natural log function. And so if we say 4x, and so you've got a key on your calculator, which is it capital or lowercase? Is it capital ln or lowercase ln?
Capital.
It's all caps? Okay. So that ln there means the natural log function, and for x greater than 0, we can say that y equals ln of x if and only if, and here's where the e comes into play, if and only if x equals e to the y power. So this looks a lot like our log function definition. It's just got e in there. So think about ln and e go together, right? And so that means that f of x equals log to the base e of x is the same as ln of x. So when we say ln of x, what we actually mean is a logarithmic function with the base e. And this is called the natural logarithmic function, natural log function. And so, just since I don't have a watch and I'm losing track of time. What time is it?
Almost 11:40.
Yeah, so we got it's 11:36. Give me those 4 minutes. All right. Painting the worst possible picture for me. Take your name off the board. No. Just know that everything we learned about the log function applies to the natural log function. So all of these properties here, right? I could take all of these, and I could replace them with, I could replace log a with ln, right? So if I did properties of natural log, I can say ln of 1, and I would take my a here and change that to the base for the natural log function, which is what? I feel like kind of awkward standing in this position here, guys.
Is it E?
E, yes, right? Because the natural log function has a base of e, right? I think you're already up there. All right, so am I going to do this on everything? Yeah, I'm going to do this on everything. So everything here, just to save me some time, I know it's not going to help you at all, but everywhere I've got a, if I've got log a, I'm going to replace that with ln, and wherever I've got a by itself, I'm going to replace that with e. right? And so we could say e to the ln of x. So I just want you to see that all of these properties still apply here, but with e in there, right? And natural log in there. E to x equals x, e to ln of x equals x, yep. And so this last one here, ln of x equals ln of y. Then we know x equals y. So if you understand it with the log, then you can understand it with the natural log function, as long as you remember that the base is e. Okay? So there's probably some way on your little note card that you can combine these together, right? So that you don't have to take up space by writing them down twice. So I'm not going to go through the examples with that because, like I said, it works exactly the same. It's just if you've got the natural log of something, you're going to use the ln key on your calculator instead of the log button on your calculator. Okay? Any questions about that? Excellent. So then, let's move on to section 3.3, where we learn how to change the base. All right, so the change of base formula, like I said, your calculator only has a log and an ln button. And what is the log button? What's the base on the log button?
A.
Huh? Well, not A. 10. So the log button is 10. So Diego and Stephen, you try, buddy. All right. You try. Give some effort. And the ln button has a base of what?
E.
E. So those are the only ones that we can do just directly on our calculator, right? So we need to, it's helpful to know how to change the base. Change of base formula. All right? So if we let A, B, and X be positive real numbers, and we say A cannot equal 1 and B cannot equal 1, then we can say the following is true. So if we have something to base B, wait a minute. Is that right? Did I write that down right? Oh, sorry, we're converting log A of x to base B. So if I want to convert log of base A of x to base B, then I would say that's log of base A of x is equal to log B of x over log B of A. Now again, why is this useful? Well, it's useful because our calculator has base 10. So let's convert log A of x to base 10. What would that mean then? Log base A of x, we convert it to base 10, we've got log base 10 of x over log base 10 of A. So that we can plug in our calculator. And same thing with base E. We can say log base A of x equals ln of x over ln of A. So if I ask you to find the log base 4 of 25, give me the decimal answer for that, you got two options for punching that in on your calculator. How would you do it?
Log 25 over log 4.
That's right. So that's one way, right? You just hit your log button, which equals log 10, right? Log 25 over log 4. That's exactly right. And, oh no. Sorry, just like, your name, did I tell you that? I got like a bunch of students that are similar to yours, and I don't know, just draw a blank. All right. And then what's the other way that I could do this?
Can you use the natural log?
I can use natural log as well, right? So I can also just punch in ln of 25 over ln of 4. So try that real quick on your calculators and make sure you get the same number, whether you use the log button or the natural log button. And you should, because in both cases we're just using this change of base formula. Get the same thing? Cool. So that's super handy when you want to use your calculator. And so like I said before, we didn't have a way to we didn't have a way to graph something like log base 4 of 25, right? We had no way to graph that. Or if this was like log base 4 of x. We could graph that, but now we can, because we can put in our on the graphing portion, y equals, we can enter something like this and it'll show us the graph of that, right? So now we have a way to do that. Excuse me, any questions?
When I put them in, I didn't get the same number for the ln of 25 over ln of 4.
You don't get the same number?
I didn't get the same number.
Really? Everybody else did?
Yeah.
Must have made a mistake somewhere. Try it with parentheses. Do log 25, do parentheses around that divided by log 4 with parentheses around that. Did you guys have to do parentheses, or did it do okay without
Well, it
parentheses?
says log, and then mine comes up with a.
Does it come up with a parentheses for you?
And then
And then I closed it with parentheses.
Okay, try it one more time. Everybody, so what do you get when you do log 25?
If I just plug it in without closing the parentheses, I got 1.6183 and a bunch of other numbers.
Okay.
0, 0, 2.
Divided by what's log of 4?
Oh, you want just log 25?
Yeah, I'm sorry, I just wanted to.
Oh, okay, yeah. So just log 25 without closing the parentheses is 1.3979.
Okay, we'll just leave it at 1.398. Just give me 3 decimals. What's the log of 4?
0.60.
0.60. Alright, and then natural log of 25?
3.218.
Alright, and natural log of 4?
1.386.
I mean, I just did that in my head. That's clearly the same number. No, just punch those numbers in. You get basically the same number if you do that. 1.398 divided by 0.6. Looks like that would be about the same thing as 3.218. That's you get the same thing?
Yeah.
Okay. So you must have entered something wrong, because I just wanted to make sure there wasn't some kind of wacky setting that he had that made your log and natural logs give you different numbers. But it looks like it's calculating those properly. So I would just say, give it another shot. It should work for you. If it's still not working, then come see me after class and we'll try to figure that out. Alright, so let's talk about some important properties of logs. The product property, the quotient property, and the power property. Alright? So the product properties of logs, they give us the stipulation here that A is a real number, and A cannot equal 1, and N has to be a real number, is real. Alright, so if those are true, and U and V are positive reals, then we can say the following. The product property says that log of U times V is the same as log base A here. Log base A of u times v is the same as log base a of u plus log base a of v. All right, that's the product property. So if you've got two things multiplied together, the quotient property. If you have log base a of u divided by v, then you can say that's the same as log base a of u minus log base a of v. And then finally the power property. Man, my allergies were giving me a fit all weekend. I'm feeling better, but I don't sound like it. N equals n log a of u. So if you've got something raised to a power of n here, then you can take that power and move it to the front and multiply the whole log times that power. Now just realize again, since the natural log is just a logarithmic function with a base e, then all of these also apply to the natural log, right? So I can say ln of uv is equal to ln u plus ln v. Ln of u over v is the same as ln u minus ln v. And then ln of u to the n power is the same as n times ln of u. All right. Any questions about those? All right, so we can put all of this stuff together. We can do some quick examples, but I really feel like these are kind of straightforward, right? Like if we had, let's see. Well, they have like expanding in. You can expand some, so you could say log 4. Just make sure you understand log base 4 of 5x cubed times y. Because of all of that, because of what we just saw, these are all multiplied together, right? 5x cubed times y. So we could bust that up into log base 4 of 5 plus log base 4 of x cubed plus log base 4 of y. Does everybody see that? And then we could even change this one here further and change this middle one to what? Based on the power property.
To 3 log base 4 x.
Yeah, so you just take the power and you move it to the front. You multiply the whole thing times that. All right? So make sure that you understand that, that you're able to follow that process. And they may give you some where you do like the reverse of that. So what if we had something like this? 1/2 log base 10 of x plus 3 log 10 of x plus 1. Right, if we look at something like that, well, we know with those numbers in the front that we can turn those into powers, right? So then I could rewrite this as log base 10 of x to the 1/2 power plus log base 10 of x plus 1 to the 3rd power. You guys follow that? Does that make sense? Yeah? And so then, because this is multiplied together, I could say I could put my log base 10 out front here, and I can, since this is added together, I can do the reverse of what I've got right here and say that's the same as these multiplied together. So I can say I'm going to rewrite x to the half power as square root of x times x plus 1 cubed. So I could rewrite that whole thing like that. You guys see how I was able to do that? Kind of weird, but
Yep.
Yeah.
all right, the properties allow you to do that. All right, so that's important when you get to section 3.4. All right, we put all of this stuff together and we start solving equations that are exponential and log functions. All right. So in section 3.4, example 1. We've got some really simple ones, right? Some simple equations. We've done some of these before. Let's do log 4. Let's do the second one. Log 4 base 4 of x minus log base 4 of 8 equals 0, right? Don't forget that we can use all the stuff we've been doing for years now with algebraic functions, and we could just move the log 8 over here and take away the negative sign, right? So this is the same as log base 4 of x equals log base 4 of 8. Does that make sense to you guys?
Mm-hmm.
Simple, right? And so now one of the properties that we learned when we were looking at the properties of log functions is that if this is true, then we know that x just equals 8. Right? So we're using all of this stuff, right? You're gonna want all of this stuff. On your quiz, I'm gonna let you do this on your quiz again next time. You can have a note card that has all the properties that we just talked about. And you can use those on the quiz to solve these equations and rearrange equations and all that. Yes?
So next we have a quiz on all of Unit 3.
It'll be of, yeah, you haven't had 3.1 yet, right? So,
Are we just going to do a unit test next week, or are we going to just use like a normal quiz in class?
no, we're just going to do the normal quiz in class.
Okay, so
Because I want to give you guys an opportunity to do this on a quiz before I give it to you on a test, right? So we're going to have a quiz over it first.
And then we're going to have a unit test on 3.1. I mean 3.
You will have a test on 3.1. So I'll give that to you the following week to take home. So I'll give you a break between, right, you'll take a test this week.
Okay.
And then I'll give you a break on taking a test next week. You won't have to take a test the following week, and then we'll do chapter 3. But these are kind of cool. I mean, if you're a weird math person, right? I think these are kind of cool. But you're trying to figure out how to kind of break these things down and solve them. So, like, if you look at an equation like this, moving a little further in the chapter, 4e to the 2x power minus 3 equals 2. And so the first thing, again, I'm looking at this as an algebraic equation, so I'm going to move my 3 over here, and I'm going to say this is the same as 4e to the 2x power equals 5. Right? That's just stuff that we've always done. Again, if we're trying to drill down and get to that x variable and solve for that x variable, the next thing I'm going to do is try to get rid of this 4 in the front here. So I'm going to divide both sides by 4 to get e to the 2x power equals 5/4. And so here's something that you've got to realize. You know how I told you earlier when we were looking at some of these properties, I said think of the log as sort of undoing the exponential. Think of the natural log as undoing the exponential with the e in it, right? So if I take the ln right here, if I take the natural log of e to the x, and also, let me do this on the next line now, sorry. If I take the natural log of e to the 2x and set that equal to the natural log of 5/4, this ln cancels out the e here, and so we're just left with 2x on this side now. Does that make sense? And now I've got now I'm just going to divide both sides by 2 to get x all by itself. So x is what I'm going to plug in my calculator is x is the natural log of of 5/4, all of that divided by 2, right? And so I'll get some decimal value. When I punch all that in, it's basically equal to 0.11. All right, so when you're solving these things, there's a little chart, there's a little strategy section over in the bottom of page 210 that says, that explains how you can use the one-to-one properties, or you can apply you use the trick of applying if it's an exponential equation, then write it in logarithmic form. Or if it's, and that's what we had here. We had an exponential equation, we rewrote it in log form, which gave us the ability to get rid of the exponential, right? And then solve it. And then if you have the reverse, if you have a logarithmic equation, use the exponential form to get rid of your logarithm. And so those are kind of your steps as you work through solving for the particular variables. And so I really think you guys are going to understand that as you go through the chapter. But what we'll do is I'll give you an opportunity to answer some questions next week before we take the quiz. Since we're cramming all this into one, right? I'll give a little bit more time to answer questions for the quiz, it'll be over the whole of chapter 3. All right. So I can give you a couple of problems, right, that really sort of test your knowledge over all this stuff now that we're sort of putting it all together. Mm-hmm. Okay, does that make sense to everybody? Yes, sir. All right. I'll send out that homework assignment. How we get a little time? Are we out? As soon as you put away your bag, unless we put away your work. Well, let me do that. Yeah, so we're right. All right, you guys have a good day, and let me know if you have any questions. There's a lot of examples that I didn't have time to go through in section 3.4. But they're pretty straightforward. If you'll just consider the properties that we've learned and read through those, I think you'll understand. All right? And have a good one.
Are we going to get less problems?
What?
Are we going to get less problems? Like per lesson?
Are you talking about less problems on the quiz?
On the homework.
On the homework? Oh. Yeah, I'll look at maybe reducing that. Just a little bit. Because I want you to see all the different possibilities so that you're not surprised. Huh? Yeah, now that you know how to do the change of base formula and all, you can check stuff with graphs on your graphic calculator, and yeah. You don't want to get to decimal. All right, have a good one, guys.
Thank you.